If I'm drawing a right Riemann sum, instead of starting my rectangle on the left, I'm going to start them on the right. So I'm going to use this point and draw my rectangle. So here I've drawn my 8 rectangles using right Riemann sums. I've gone from the right to the left and drawn my rectangles. Okay, so a right Riemann sum, we start on the right and go to the left. So now, if I wanted to find the height of this rectangle, wouldn't I plug b into the f of x to figure out what this length is, what my y length is to go up to my curve? And I start on the right and draw my rectangles to the left. They will tell you how many rectangles they want you to separate this thing into, and then you will have to figure out the distance for the width of each rectangle, and then you'll plug into the function at each of these x values to find the height of each rectangle. And the more rectangles we do underneath the curve, the more accurate our area under the curve is going to be. We're going to take this example. It says estimate the area bounded by the curve and the x-axis on the given interval using the indicated number of subintervals by finding A, the left Riemann sum, B, the right Riemann sum, C, the midpoint Riemann sum, and D, the trapezoid rule. And we're going to use the function y equals square root of x on the closed interval from 0 to 1, and we're going to subdivide it into 4 subintervals. And those subintervals are going to be of equal width. So we're going to take this to the whiteboard, and in today's video we're going to do the right Riemann sum. The next video we do will be the midpoint Riemann sum, and the last video, or the video after that, will be on the trapezoid rule. So now we're going to do the same thing using the right Riemann sum. And one thing about this is if they ask you to do the left Riemann sum and the right Riemann sum for the same graph, you know that you can use the same heights that you used on the right Riemann sum with the left Riemann sum, and vice versa. You do not have to do all the math again, because these heights are not going to change whether you're going from the right or the left. They do stay the same, so that's nice. One thing that will save you time as you do these. So with this one, we're looking for the right Riemann sum this time. So now I'm going to draw my rectangles from the right side to the left side. So I'm going to start here, draw my rectangle. So there's the first one. The next one, I'm going to start here, draw my rectangle. For the third one, I'll start here and draw my rectangle. And for the last one, I start here and draw my rectangle over until the end of the intervals. So looking at this, if they ask you if this is an over or an underestimate, you can say, well, this is an overestimate, because not only are we accounting for all of the area underneath the curve, we're also accounting for these extra portions in these rectangles. So this is going to be an overestimate. And it's okay to assume that the real answer, the exact answer between 0 and 1 for the square root of x, the area under the curve, is going to be somewhere between your left Riemann sum and your right Riemann sum. If I look at this, again, the width of all of these rectangles is still 1/4, and I can get the height of each of the rectangle by looking at where I've drawn that height up. So for the first rectangle, the width is 1/4, and the height of that rectangle is what I get when I plug 1/4 in to the square root of x, which would be 1/2. Again, the width for the second rectangle is 1/4. The height, when I plug in 1/2, is going to be 1 over square root of 2. The width for the third is 1/4. The height is what I get when I plug in 3/4. So that's square root of 3 over 2. And then the last rectangle would be 1/4 times 1. And so I have 1/8 plus 1 over 4 square root of 2 plus square root of 3 over 8 plus 1/4. And I could put that in my calculator and solve it. And when I do that, I end up with 0.768 square units. And again, that would be an overestimate. So if I use the left Riemann sum, the right Riemann sum, I know the actual area under the curve is going to be somewhere between those two, because the left Riemann sum was an underestimate and the right Riemann sum is an overestimate. And you can tell that by looking at the pictures. Sometimes, instead of having to draw the graph like we did on the whiteboard, they're going to give you the graph and just ask you to estimate the right Riemann, left Riemann, midpoint, and trapezoid rule. And so when they give you the graph, it makes it very simple. It's a very simple process. In this video, we're going to do the right Riemann sum. For the right Riemann sum, notice I'm drawing from the right-hand side of each rectangle. Each of the widths is 1, and then their heights are different. If I take the areas of each of those rectangles, I would have 3, 4, 3, 2, and 1, because we're multiplying the width times the height for each of them. So 1 times 3 is 3, 1 times 4, 4, and so on. So if I add the area of those rectangles together, I will end up with 13 square units. On this one, it says, oil is leaking out of the tank. The rate of flow is measured every 2 hours for a 12-hour period, and the data is listed in the table below. The time in hours goes from 0 to 12. The rate, which is gallons per hour, that is the amount of oil leaking out of the tank, goes from, well, 40 to 8, and we can see here that we're going to be able to graph those ordered pairs pretty easily. It says A, draw a possible graph for the data given in the table. B, estimate the number of gallons of oil that have leaked out of the tank during the 12-hour period by finding a left Riemann sum with 3 equal subintervals. C, estimate the number of gallons of oil that have leaked out of the tank during the 12-hour period by finding a right Riemann sum with 3 equal subintervals. So we're going to do A, we're going to draw the graph, we're going to do and C, the left and right Riemann sum. Part D we will do in the next video when we're dealing with midpoint Riemann sum, and part E we will do in the video after that, where we're dealing with the trapezoid rule. So the first thing I'm going to do is graph that function. So here's a little graph of what we're dealing with here, and we need to draw the lengths from each of these up to the ordered pair associated with it. So that's going to be the next thing that I would do for my graph. So in this part, we're going to do the right Riemann sum, so we're going to do part C. And they're telling you to estimate the number of gallons of oil that have leaked out of the tank during the 12-hour period by finding the right Riemann sum with 3 equal subintervals. So just like I did for the left, I'm going to do all 3 subintervals, and then I'm going to do all 6 subintervals, just so you can have 2 different examples of how to tackle this problem. So here is my picture blown up a little bit. I'm using 3 subintervals using the right Riemann sum. So this time, if you think about the width of your rectangles, again, the width of each rectangle is going to be 4. So that is staying consistent. And then we're drawing this time from the right side. So if I draw from the right side, these are the rectangles that I'm going to get. So if I find the area under the curve for those 3 rectangles, for this one, I'm going to have the width is 4 times the height. We're finding the height, it's touching the function when x is 4. So when x is 4, the height is 36. For the second one, the width again is 4. The height is where it touches the function at 8. So that would be at 26. And for the third one, the width again is 4. And the height at 12 would be 8. I'm going to plug that into my calculator. And my estimate would be 280. And again, for my unit of measure, gallons per hour over hours would be gallons. So it's losing 280 gallons over the first 12 hours. And you can see this is quite a difference between, there's quite a difference between 3 subintervals and 6 subintervals. You're going to notice even more differences between the midpoint rule and the trapezoid rule. So next I'm going to separate this into 6 subintervals so that we can see that that would be a closer estimate to what the actual area under the curve would be, just to give you another example. This time I'm going to draw my rectangles from the right-hand side. My rectangles straight across from the right to the left. And I do these as carefully as I can. They're not going to be perfect if we're drawing them by hand, but we do the best we can. So looking at this, I need to find the areas of each rectangle. Again, each rectangle has a width of 2. This time though, when we're looking at the height of each rectangle, we're looking at the right-hand side of where it crosses the function. So this would be a 2 times this height, and at 2 we were at 38. So 2 times 38 would be 76. 2 times at 4 we were at 36, that would be 72. 2 times at 6 we were at 30, so that would be 60. 2 times at 8 we were at 26, so that would be 52. 2 times at 10 we were at 18, so that would be 36. And 2 times at 12 we were at 8, so that would be 16. We would add all of these areas together to get the estimated area under the curve. I end up with 312. And again, hours times gallons per hour gives me gallons. We can estimate that 312 gallons have leaked out of the tank. Now, if you compare those two answers, if we look at this one, we notice here that our rectangles are above where that curve is. So we're going to have an overestimate for this one. So 376 gallons is a little bit over what the actual number of gallons is. If we look at this one, notice where we drew the curves here, these are all underneath the curve, so this would be an underestimate for the area under the curve. So this is 312. So we know our answer is going to be somewhere in between 376 gallons and 312 gallons. So you can, using graphs like this, by drawing a very simple graph, you can figure out whether it's going to be an over or an underestimate, and you can get a pretty good idea of what the area is going to be underneath your curve within that specific interval.